Hello friends. In the previous lecture we looked into the mathematical aspect of the Fick's first law. So what Fick's first law allowed us to do is it allowed us to understand a numerical operator called gradient. So if you could recollect, this gradient, it governs, in the context of Fick's first law, it governs the flux that is introduced into a system when the concentration within the system depends on the position. So when you have a system that is heterogeneous, the concentration depends on the position or the point that you consider. So therefore the flux is introduced, and this flux is rather governed by the negative of the gradient of concentration. And the gradient, when you take a gradient of a function, the output of it is a vector. Now the expanded form of this gradient, assuming that we are considering a three-dimensional system, will be of this form, that is the partial derivative of concentration with varies with the position being described in terms of x, y and z. So dc by or dou c by dou x, since the outcome is a vector, we are associating it, that is the dou c by dou x, to one of the orthonormal bases, that is I vector here, and secondly dou c by dou y. Since it is a three-dimensional system, we have x, y and z associated, and this partial derivative is associated with another basis, and finally we have dou c by dou z, which is associated with another orthonormal basis, that is k vector. So what essentially we have is, we have a gradient, and this gradient, it induces a gradient in concentration and this induces a flux. And now since this is what governs the flux and this is what gives the vectorial notation to the flux, so it means the flux is associated with the specific direction. If we graphically represent the concentration at a point that we are interested in is this, so this is the point or the concentration that we are interested in. So for this case, let us assume a two-dimensional system. X and y are the spatial coordinates and c is the concentration, and this is the concentration that we are interested in. And along the different directions we have different gradient that are present. So along this direction, say for instance, if we assume this direction to be a direction, there is a gradient present, and in this direction there is a gradient present, and in this direction there is also another gradient that is present. So in this, so we have our A direction, B direction and D direction. In each of these directions we have a different gradient or different difference in the concentration when you move along these different directions. So when you move along the A direction, there is a variation in the concentration. In the B direction there is a variation in the concentration, and the C or the D direction, because since we have already represented C as concentration, we have considered another direction to be D. So as you move along the D direction, there is another difference in the concentration changes. Now the flux, it adopts a concentration. Even though the gradient can be found in all these three different directions, the flux, it confines itself, it restricts itself. The flux is primarily observed in one of these three directions, and that direction is estimated by considering the magnitude of the gradient in all these different directions. So what we have here is, we have three directions that are represented by three vectors. So we have direction A, direction B and direction D, and these directions are represented by these vectors, and these are not unit vectors. So what we have done is, we have considered a concentration that is of interest to us at a point, and we have considered three different directions along which there exists a non-zero or non-trivial gradient. Along the three directions there exists a definite gradient, and we want to know along which direction will the flux be introduced. So we have these three directions, A, B and D. So this is A, we have B and D, and these are three different directions, and along all these three different directions we have non-zero gradient, but the flux will be along largely will be oriented towards a specific direction, and we want to know what specific direction it is. Now the gradient along the A, the magnitude of the gradient along the A is the length of the A vector. So in this representation, the magnitude of the gradient along the A direction is the length of the A vector, and similarly the magnitude of the gradient along B is the length of the B vector. And similarly, the magnitude of the gradient along C is the length, or along D is the length of the D vector. So we have considered three different directions, and in three different directions there exists a gradient for concentration, there exists a non-zero gradient for concentration, and the magnitude of these gradients are rather represented by the length of these vectors. So these three vectors are non-unit vectors, and the length of these non-unit vectors indicate the magnitude of the gradient, the slope of this function along this direction. Now, we saw in our previous lecture, by involving the directional derivative, or by considering the directional vector, we saw that the flux, it orients itself. The flux is largely found in the direction of the maximum gradient. So the direction of this flux is along the direction of the maximum gradient. So therefore, in this case, what we essentially have is, we have the flux oriented along this direction here. So even though for the point that we have considered, there exists gradient in three different directions, the flux will be induced in a specific direction, and that specific direction would be the one wherein you have the largest magnitude of your gradient and concentration. The largest slope is along which, or the direction of the largest slope is where the flux will be introduced. Along the direction of the largest slope is how the flux will be introduced, or the flux will flow. The flux of concentration will flow. This we can derive it. We have showed us, and it can be derived by considering the directional derivative. And what essentially we do is, we take the dot product of the flux with itself, and when you consider the direct product of the flux with itself, we identify that the direction of the flux will be along the direction of the largest gradient, or the magnitude of the gradient, the largest magnitude of the gradient, or the largest slope. So this is something we saw in our previous lecture. Now, what we have essentially done is, when we say that the gradient of the concentration that varies with the space, it yields a vector, then there is a skeletal form associated with this symbol here. There is a skeletal form associated with this symbol here, and from which we translate this scalar value into a vector. So there is a skeletal form associated with this, and therefore when you couple this operator to that of the concentration function, they ultimately end up with a vector. This skeletal representation of the gradient is of this form: I dou by dou x plus j. So I vector, one of the orthonormal bases, j again another orthonormal basis, and k. So this is the skeletal form of this nabla or grad. So one other way of writing this would be grad of concentration, and the skeletal form of this nabla grad is of this form here. Now it is possible for us to write a vector in the form of a column matrix, and therefore another way of writing the gradient would be in the form of a column matrix. So this is one way of representing the gradient of, or the skeletal form of the gradient. And now what essentially we can do is, we can use this and we can couple this with any functions that we need, and then to estimate its corresponding gradient. Now this is rather the numerical operator that allows us to estimate the gradient of the concentration that we have used to estimate or quantify the flux when we are considering a heterogeneous system. Now there is one property that allows this, or that enables the use of this gradient vector or this numerical operator to translate the Fick's law into, or to rather arrive at the entire relation of the Fick's law. So far whatever we have considered is, the flux that is introduced is proportional to the gradient of concentration. So this is all we have considered so far. So there is of course a negative sign that is included to introduce the convention. So what essentially we have is, the flux is proportional to the gradient of concentration. What we have not considered, this is not, even though this gives us a framework for the Fick's first law, this is not entirely the expression of the Fick's first law. The Fick's first law is a relation. So Fick's first law, it definitively tells us how much will be the flux when you have a gradient and concentration. So when you want to translate this proportional relation to that of an equation, then you need to introduce a constant of proportionality, and that usually is what we refer to as the diffusivity. And this diffusivity, it varies with the components. Say for instance, when you have carbon, the carbon has a specific diffusivity. Again, it also depends on the matrix in which the carbon is present. So this diffusivity, it varies with the alloying element, and also it varies with the system in which it is present. So it depends on, so in case of FeC, the diffusion of carbon, it is dependent on the carbon and the system in which it is present, because in FeC often the carbon occupies an interstitial lattice, so therefore, or interstitial position, so therefore the diffusivity varies. So it is something that it is a parameter that makes this expression rather quantitative in nature. Instead of being just a qualitative expression, this diffusivity, the constant of proportionality, it ensures that there is a quantitative aspect to the Fick's first law. So when you introduce the diffusivity, then the entire expression would adopt a form like this. So what we have essentially done is, we have now moved away from the framework, the outline of the Fick's first law, to its expression, its definite expression. And in that definite expression, in addition to the concentration, we need to include the proportionality constant, which is the diffusivity here. Now what essentially this diffusivity, at least in this straightforward case, in this simplistic case here, is this diffusivity is a constant, and it's a material constant, meaning it depends on the alloying element that we consider. Again, depending on what system we are considering, the value of this diffusivity varies. So essentially what it means is that it is possible for us to take the D outside. This being a constant, it is possible for us to take it outside, and we can go back to relating this operator, the gradient operator, to that of the concentration, which is the only variable that varies with the spatial position. So assuming that the diffusivity is constant and it is a material constant, it does not change with position, what essentially has been done is, even though the accurate form of writing the Gibbs expression is in this manner, since we have assumed that, or often when you consider a simplistic case of a gradient in a system, since the diffusivity is dependent on the material, it assumes a role of a constant, and it is possible for us to take it outside, and therefore we can directly associate the gradient operator to that of the concentration, which is the only variable here. Now this indicates that there is a special relation associated with this gradient operator. So there is a special feature associated with the gradient operator, meaning this gradient operator, it acts as a linear operator. So one feature, or one way we know that the gradient operator acts as a linear operator, is it allows us to take the constant when the constant is coupled with a variable with a spatially varying parameter. Then it is possible for us to take the constant outside and associate this operator directly to that of the concentration. Secondly, that is also a key feature of this gradient operator, that is, when you consider the gradient of two concentrations, say for instance concentration of carbon and the concentration of manganese. So we want to know the coupled flux of the carbon and manganese. When you have a system, a ternary system of FeCMn, a manganese steel system, and this system again is heterogeneous, depending on the position, the concentration of carbon and also the concentration of manganese varies. So in that case, when you want to find out the coupled flux associated with such an heterogeneous system, you need to find the gradient of both coupled carbon concentration and manganese concentration. So this operator, this gradient operator, can then be handled. So in this case, wherein you have not just one concentration but two concentration, and both these concentration, they vary with the position, they vary with x, y and z axis in the three-dimensional case. Now how we can handle such a ternary system is, we can consider the gradient of carbon separately and sum it up with the gradient of the manganese separately. So what essentially we can do is, even though we need to know the combined flux of carbon and manganese for a FECMN system, since this flux is governed by the gradient of concentration of carbon and manganese, and this gradient is a linear operator, it allows us to handle the carbon separately and manganese separately and then sum it up together. So this is possible because our gradient is a linear operator. So even within the context of the Fick's first law, one feature of this gradient allows us to handle the system in a more straightforward manner. So one is, when our function is associated with a constant, because our gradient is a linear operator, it allows us to decouple the constant and the function and impose the gradient within or into the or couple the operator, the gradient, with the function alone. And then similarly, in a second case, in a more convoluted case of a ternary system, wherein instead of having only one spatially varying concentration, when we have two spatially varying concentration, and when it is our motive to find the combined flux, the gradient being a linear operator, it allows us to handle both these concentrations, spatially varying concentration, separately and sum it up together. And ideally what we end up having is, in this case, now we are able to estimate the flux, that is the combined flux that is associated, that is introduced when we have a gradient in concentration of carbon and in the concentration of manganese simultaneously at any given moment. Now, what essentially we have done is, we have then considered, instead of considering one concentration, we have introduced another concentration. We have included, in addition to one function, we have included another function as well. Now, what we have seen in our previous lecture is that apart from function, it is also possible for us to identify the derivative of the set of data points. So when you have a set of data points, it is possible for us to have or to estimate the derivative of such a set of data points. So when you have x1 and correspondingly you have a function, and so if you treat this as an input and this as an output, so you have in this case created a set of data points, and using which you will be able to develop a function. Even if not, you will be able to derive, or you will be able to find the derivative of these set of function. Now this is rather a straightforward function, because we have one variable or the one independent variable, and this one independent variable, it governs the dependent variable. Now often, again, we saw an example of how or relating the yield strength to the multi-component alloys. So when we have, say, an alloy that we often see in an application that comprises of numerous concentration, say for instance, if you have x1, x1, x, y, z. So these x, y, z, they indicate different concentration and or different alloying elements, and the yield strength of these alloy is dependent on all these alloying elements. So what essentially we have is, we have one independent variable, the other independent variable, the other independent variable. So x is one alloying element, y is another alloying element, z is another alloying element, and ultimately all these three alloying elements contribute to the yield strength of the material. Now in this case, the data set that we have would look like something like this: x1, y1, z1, and you have the yield strength that is dependent on x1, y1 and z1. So this will continue, will have n such data set or n such data points, where all these three are contributing to the yield strength of your ultimate alloy. Now in this case, it is possible for us to estimate the derivative with respect to each of these concentrations. Now what it means is that if it is possible for us to estimate the derivative with respect to each of these concentration, what it ultimately means is that it is possible for us also to estimate the gradient of the data points. So it is possible for us to estimate the gradient of all these data points. So what I mean by that is, so if we have such a function, such a relation, it is possible for us, from this data point, it is possible for us to estimate df of x1, or rather df of x, y and z, or dou f of x, y and z, and dou of x. And this would be I1 vector. So what is possible for us to find the gradient of this data point, and if you consider the gradient, how it looks like, it can be expressed in this manner, wherein you are considering the derivative of the function with respect to the first variable and associating it to an orthonormal basis. So we start with this, we introduce we consider the partial derivative of the function with respect to one of the variable and associate it to one of the orthonormal bases. And we do it for the second independent variable, that is dou of x by dou of y, we associate it to the next orthonormal basis. Now we introduce it to that of we consider the third derivative, the derivative of a function with respect to the third variable, we associate it to that of the another orthonormal basis. So what essentially we have done is, we have related, or we have expressed the gradient of a data points, a set of data. We have a set of data points, and from that set of data points we have identified the gradient of these set of data points. And the expression, though it looks similar, it looks the same, what essentially we have to do is, we have to go back to the first principle estimations of this partial derivative, and we need to understand how each of these functions vary when we consider the change in the x alone. Now the reason we need to consider this is because this particular data set, it pertains to three alloy, or we have here three alloy elements. So this system pertains to three alloying elements, or it's a quaternary system. So this system comprises of three alloying elements and one base metal. So the total number of components that are present here is three components, or rather four components, and out of which, since we have three independent components, this way of representing became easier for us. If we go beyond such a system, when we consider a system with 5 components and beyond, 5 plus components, what essentially then we have is, we have, for instance, so x, y, z and z1. So these all will be our independent variable, and the dependent variable the value of the dependent variable will depend on each of these variables. So it will depend on x, y, z and z1. So you have now a 5 component system, a 5 component alloying system, and then in that system what you essentially have is 4 independent variables, x, y, z and z1. The yield strength depends on all these 4. Now when you want to find the gradient of such a system, what essentially the trouble we will face, or the difficulty we will face in expressing the gradient of such a system would be, so we would be able to write it with dou f by dou x and associate with one of the bases. We will be able to consider the partial derivative of all of these with respect to all of these variables, the partial derivative of the function with respect to all of these variables. So we have considered the partial derivative with respect to x, with respect to y, with respect to z and z1. Now we can relate this to an orthonormal basis of I, we can relate this to j, and we can relate this to k. But we also need another orthonormal basis for this partial derivative, which we have not so far defined. So what essentially we mean is, when we extend the gradient, our understanding of gradients to data point, then we need to accommodate, we need to have a system that is multidimensional in nature. Our space that we create, the vector space that we create, needs to be multidimensional in nature. So what it means to have a multidimensional vector space is, the multidimensional vector space, depending on the dimension of this vector space, the orthonormal basis, the number of orthonormal bases that we have also increases. So in this case, this is not possible because this is rather restricted to a 3-dimensional vector space, or a 3-dimensional space. The basis of I, j and k, these largely they stem from the 3-dimensional space. But what we need is a 4-dimensional vector space. In order to find the gradient of this function here, this 5-component function here, in order to find the gradient of the 5-component function here, or a 5-component alloy element here, what we need is a 4-dimensional vector space. So when you have a 4-dimensional vector space, what it essentially means is, we need to have sufficient amount of orthonormal basis. So we need to have 4 orthonormal bases. So it should be 1, I1, I2, I3 and I4. So when we are largely focusing on a given function in a 3-dimensional system, so the case we started off with is concentration. We considered a 2-dimensional concentration, so it means it is possible for us to represent it in the form of rather a 3-dimensional structure, and we were able to express, since the concentration was dependent only on x and y, we were able to express it rather in a direct manner into the gradient and express it in the form of a vector like this. And again, in 3-dimensional case, it is possible for us to express it in the form of a vector like this. However, when you move away from considering the gradient only as the partial derivative with respect to the spaces, these 3-dimensional spaces, and when you want to use the gradient or apply the gradient to the set of data points, the data points, they do not always restrict itself to a 2-dimensional or a 3-dimensional space. The data points, they do not always restrict themselves to a 2-dimensional or a 3-dimensional vector spaces. The number of independent variable, when you consider a set of data points, particularly data points that are relevant to us in employed in an application, they have numerous variables associated with them, and depending on their independent nature, or depending on the number of independent variables that are involved, the dimension of the space that is required for us to handle the gradient of these data points vary. Again, in this case, we are considering a 5-component alloy, and therefore we have 4 independent concentration and an output that is dependent on all these 4 independent concentration. Now, when you want to find the gradient of this function, and when you want to have the direction of this gradient, then what essentially we have is, when you want to know how the concentration is rather distributed, or when you want to know in which direction the flux is going to be, what we essentially need to know is, we need first to have the sufficient vector space. We need to consider a adequate vector space that helps us, in addition to finding out the derivative, or in addition to finding out these individual partial derivative, it also helps us in finding out the appropriate direction. It helps us to build a vector function for this gradient of data points. So in order to have a meaningful vector function for this gradient that is well beyond the 3-dimensional spatial coordinate system, in that case, we need to build a multi-dimensional vector space, and when we need to consider a multi-dimensional vector space. So when we say we need to consider a multi-dimensional vector space, what it essentially means is, we need to have the sufficient number of bases to represent this multi-dimensional data space. And now, when you have this multi-dimensional vector space that is rather represented by the different bases, or that can be either depicted or represented by these different bases, then what we can do is, we can express the gradient of such a function or such data points, the gradient of such data points, such multidimensional data points, as this. So f by dou x, I1 vector, dou f by dou y, I2 vector. So I2 basis, dou f by dou z, I3 basis, and dou f by dou z1, I4 basis. So what essentially we have done is, in this case, we have considered not a concentration but a set of data points, and if these data points are beyond the 3-dimensional vector space, and we had to go for a 4-dimensional vector space. And meaning, when we say that we have to go for a 4-dimensional vector space, we have to rather accommodate, or we have to substantiate it with the additional number of bases, and that additional number of bases, it helps us represent the gradient of this function x, y, z and z1. This function here, it comprises of 4 independent variables, and therefore we need a 4-dimensional vector space, and this 4-dimensional vector space is characterized by 4 different orthonormal bases. Even though it is rather difficult for us to conceive or imagine such a 4-dimensional vector space, it is rather relevant when we consider such a data point. It is possible for us to at least numerically understand what such a 4-dimensional vector space would be, and why we need 4 bases in order to describe any vector within the 4-dimensional vector space. So whatever operation that we have carried out in the 3-dimensional space can be extended to the multi-dimensional vector space. So here we have considered just a 4-dimensional vector space, and here in that 4-dimensional vector space we have expressed the gradient in the 4-dimensional vector space, and whatever properties that we have studied for or we have considered for the 3-dimensional space is applicable here. So in all these direction, in all these along all these bases, we are considering the slope of the given function, and we are associating each of these slopes to a specific basis. So we have 4 bases, and to each of these bases there is an associated corresponding slope in this expression here. Now the reason, so when we consider or when we introduce the gradient, we introduced it in a context, meaning there was a specific role played by the gradient, and that allowed us to study the gradient. So the gradient we did not study purely in an abstract way. The reason we considered the gradient is because there was a key role that was played by the gradient when we consider the Fick's first law. So that was the relevance of studying the gradient of concentration, particularly when it is dependent on, when it varies in a 3-dimensional space. Now let us see what would be the relevance of understanding or estimating. So why should we in any case have to rather find out the gradient of the set of data points? So gradient of concentration is understandable because it allows us to estimate what would be the flux. And when we say that it is important for us to understand what would be the flux through the gradient of concentration, what it means is that when you have a system of this sort, when you have, say for instance, the ferrite phase here, the ferrite phase, and when we have the austenite phase here. So generally, because of the crystal structure of the ferrite phase and the austenite phase, the difference in the crystal structure, the solubility of carbon here is lower than that of here. The solubility of carbon in alpha is lower than that in case of gamma. So the solubility of carbon in ferrite is less than the solubility of carbon in austenite. So what happens is, when you want the ferrite to grow in the austenite, then there should be a flux of carbon. So you have 2 phases, a ferrite and an austenite phase. The feature or the property that characterizes the ferrite is low amount of carbon. In austenite you have high amount of carbon. So when I say the ferrite is growing in the austenite matrix, what it means is that the carbon is moving from the ferrite to that of austenite. There is a flux of carbon from ferrite to that of austenite. Now, depending on the direction of the flux, there will be the growth of ferrite. Let me repeat, depending on the direction of the flux, there will be growth of ferrite. So supposing if I have a ferrite matrix, or a ferrite rather a precipitate in again in the context of the numerical studies, we consider this as precipitate, but even though the ferrite is not a precipitate, for this discussion let us assume that this alpha is ferrite and it is rather surrounded by the gamma matrix. Supposing this growth of this ferrite depends on the flux of the carbon. The flux of carbon, the carbon moves out of ferrite to austenite, and as it moves, the ferrite begins to grow. The carbon moves from ferrite to austenite, and as the carbon moves out, the ferrite grows. Now, supposing if we assume that the gradient is the largest in this direction, the slope is the largest in this direction, then the flux will be largely focused along this direction alone. Then what essentially it will mean is the growth will be of this form here. So the growth of the ferrite, even though there are gradient present here, since the largest gradient is in the red direction, the growth will be of this form here. So therefore, understanding the gradient in the context of material research is hugely critical, because it shows us how the phase transformation occurs, how the change in the morphology as the phases evolve occurs. Now, so that is the relevance of the gradient in the framework of Fick's law and the gradient in the material studies, or particularly in the phase transformation. Now, let us try to understand why it is relevant for us to identify the gradient of such data points. Why should we have to identify the gradient of such data points? Now, a key role of identifying the gradient is because it allows us in an operation called as optimization. So, as opposed to purely numerical operation, this optimization is also involved in data analysis and machine learning. So, what it allows us to do is it allows us to optimize our function. Now, supposing, let us go back to our for our ease of understanding, let us go back to our two-dimensional case. And in this two-dimensional case, instead of considering the concentration on how with respect to x and y the concentration varies, let us consider an error function. And this error function is dependent on, so you are doing a data analysis, and there is an error function associated with the output that you get, the model that you have developed. There is an error function associated with it, and this error function is dependent on two independent variables x and y. And the error function is of this form like this. So it's of this form like this. So we have an error function that is of this form like this. So you have a parabolic error function. Now this error function, again, it is dependent on x and y. Now what we mean by optimization of this error function is you have to reach the point here, where the error is close to zero. The error is minimal. So you have to reach a point where the error is minimal. Now, in order to reach the minimal error point, the error is minimal is what we mean by, in this case, what we mean by optimization. So in order to reach up this point, the minimal error point, what can be done is we can consider a specific point of x1 and y1, and in this point we will be able to, or we can estimate the gradient at this point, the gradient of this error function at this point. So we have an error function, we have to optimize this function. So optimization of this error function, again the error function in this context, we have a function, and in this case is an error function, we want to optimize it. So optimizing it means we have to reach the minimal most position. So we have to reach the minimal intersection of this function here. So in order to do that, you select a given point and the error associated with it, and find the gradient of the error at that point. The gradient of the error. So the gradient of the error function. Now the gradient of the error function gives us the direction along which the error is decreasing in a faster way, along which the slope is maximum. It means the direction along which the error is decreasing at a faster rate. So what we want to do is we want to reach from this point, from the point where we are in, to this point here, which is the minimal most error point. And for that, what we are doing is from this starting point we are considering the gradient of this error function, and this gives us for this point what would be the direction along which the error decreases in a faster rate. However, this direction here, if we take this direction, we will move along this direction, and we will move away from this minimal point here. If we go along this direction alone, then what essentially we will do is we will go in this direction and we will miss the minimal most point. So what we need to do is we cannot, after finding the gradient here alone, we cannot stay in this direction itself. So we need to set a definite step size. So we need to set a definite step size, and after the step size we need to locate up another point. We need to locate another point and find the gradient from that point. So what essentially you have is you have a curve of this form. You start from here, and your destination is to reach this point. This is the minimal error point, and here you find the gradient, and the gradient is pointing in this direction. Supposing the gradient is pointing in this direction. Now if you go along this direction, you miss out on the minimal most point. So what you need to do is you select the step size, and the step size it can be selected here. So it can be here, any point the step size needs to be selected, and at that step size you calculate your gradient at this point here. You start from this point here, so x1, y1, you start from this here, and you move to x2, y2 and find the gradient there. So this gives us the initial direction, and if I take the initial direction alone, I will not be able to reach my desired point. So you consider a step size, and because of the step size, now we are moved from x1 y1 to x2 y2, and you calculate the gradient at x2 y2, and at the gradient will then point you to the shortest path to reach our destination of this optimized or the minimal error point. So what essentially you do is you repeat this combination of finding the gradient and applying the step size. You find the gradient as a desired point, apply the step size and reach the next point, and find the gradient, apply the step size and reach the next point, and at this point you find the gradient again, and ultimately the gradient will lead you to the desired point. So what you have essentially found is you have found the shortest path to reach your minimal error region from a desired point, from a starting point, from a region or from a given point. You have now arrived at, you have now optimized your function, and you have reached the minimal most point of your error function, and this is what we refer to as the gradient descent optimization. It can also be expressed as gradient based optimization. So what you are trying to do is you are trying to arrive at a point. So you are trying to identify, you are trying to reach at the minimal most point of your error function. So in this case we have considered the error function. It can be any function. Now this plays a key role when we are trying to rather identify an alloy that gives us a specific desired concentration. Now we have related the concentration to the yield strength or any property of the material. Now when you want to identify, when you have a desired property and you want to know what is the composition that would give me this desired property, then optimization plays a critical role, and in that optimization the gradient based approach plays a vital role. So what we do is, while when we are using the machine learning techniques to identify which combination of alloying element would give me the desired property, we introduce a function, and for that function we use the gradient based optimization in order to identify, narrow down which concentration will give me the desired property. Now that is the significance of identifying or estimating the gradient of the data point. What it allows us to do is, when you have a set of data points and we don't know what is the efficient or the minimal most point of this data point, you have a set of data points and you want to know what is the minimal or how to optimize these set of data points, and that is in this case the minimal most point. So if we want to have a reach such the minimal most point, like in this case of the error function, what can be done is we can consider the gradient at different points, and the gradient, the progressive gradient, the gradient descent will allow us to move in a specific direction. When we move along this direction, it will allow us reach the destination in the fastest manner possible. So that is the reason why we need to consider the gradient not only for concentration but for the set of data points as well. So the gradient, it plays a role in identifying or in optimizing a given function, and this is not only restricted to a three-dimensional case such as this, but optimization is usually done in multi-dimensional vector spaces. Again, the reason this optimization can be done or needs to be done for multidimensional vector spaces is primarily because when we are considering a set of data points, particularly concentration and a property, they are very rarely can be these concentration on the properties, these can very rarely be restricted to a given system or a given three-dimensional system. So we need to have a multidimensional vector space, and when we have a multidimensional vector space and when we want to perform the optimization in the multidimensional vector space, then essentially we are considering the gradient in a multidimensional vector space. So essentially what we have seen is the gradient, it plays a role in the evolution of concentration that comes from the Fick's law. The gradient also plays a role, or it also is of a vital importance when we are considering a set of data points and finding the gradient, or when we are handling this data points and when we want to optimize this data point, when we want to have an optimization, when we want to perform an optimization. And in order to perform the optimization, what we essentially have to do is we need to consider the gradient at a specific point and involve a specific step size and need to perform the gradient as, so the gradient will give you the direction and along the direction the step size will give you the next point. So as we have seen in this case, the gradient will give me the direction, and the step size it gives me the next point to consider. By combination of this gradient and step size, we will be able to optimize the data set that we have. So the gradient, it plays a vital role both in the physical system and also in the data analysis. That's the reason why we have spent quite some time on this gradient. So we will move away from the gradient and we will try to get into the second law of thermodynamics and what the importance of the mathematical operators that are involved in the subsequent lecture. Goodbye.